Hello everybody and welcome to my 37th video. This is on the Quaternary JK and T-type flip-flops. I'll be going through the design process with you. So first we have the T-type flip-flop. We have the characteristic equation Q plus equals T plus Q modulo 4. So Q plus is the value of Q after the flip-flop has been clocked, and this is T here, this is Q here, this is Q plus. So the plus in the circle represents modulo 4 some function. And for instance, 3 plus 3 is 2 modulo 4, 3 plus 3 is 6. So divided by 4, 6 goes into 4 ones, remainder 2. So the output is the remainder when the sum of T and Q is divided by 4. Now, this is a binary design. Convert the quaternary into binary, process the signal in binary and convert it back to quaternary. So here I have the binary to quaternary to binary conversion, which I'm going to use to code T, Q and Q plus. This is T1 and T2 here, according to this truth table. Q2 and Q1 here, according to this truth table, and Q2 and Q1 plus and Q2 plus here, according to this coding. So the coding goes if x is a quaternary 0, x2 is 0 and x1 is 0. If x is a 1, x2 is 0 and x1 is 1. If x is a quaternary 2, x is a 1 and x1 is 0, x2 is 1 and x1 is 0. And if x is a quaternary logic 3, x2 is 1 and x1 is 1. These are binary, this is quaternary. Now I'm going to implement the T flip-flop using JK flip-flops. And this is the excitation table for the JK flip-flop, the binary JK flip-flop, should I say. So for example, if Q1 is a 1 and Q1 plus is, if Q1 is a 0 and Q1 plus is a 0, you get JQ1 and KQ1 of 0x, which is there. Q plus 0x. For example, if Q2 is a 1, Q2 is a 0 and Q2 plus is a 1, you get JQ2 and KQ2 is 1x, 0, 1, 1x. So that's how you derive the output, the inputs to the JK flip-flops. I'm using 2 JK flip-flops, one for Q2, one for Q1. So yeah, all these are listed as all the variables are listed according to this truth table, and there we have the truth table. So we'll go to the counter maps. Right, this is the counter map for JQ2. Here, this loop here is T1 and Q1, and this loop here is T2. So I'm going to implement this with binary Reed-Muller algebra, and the rule is if a coordinate of the counter map is looped twice, an even number of times, the coordinates are 0, and if it's looped an odd number of times, the coordinates are 1. So here I'm using the exclusive OR gate instead of the OR gate for binary Reed-Muller algebra, and this is looped twice, this coordinate, so it's a 0, and these are looped once, so it's a 1. Now this x can be 0 or 1, but in this case we're taking it to be a 0 because it's looped twice, and this x is a 1 because it's looped once. So if you, this is expression for JQ2, so if you complement the exclusive OR gate both the inputs and complementing the inputs an even number of times, it performs the same function as an uncomplemented exclusive OR gate. So I can do that just so I can use 3 hex inverters instead of 4. That's just a trick I pulled to save gates. Okay, so this is KQ2, exactly the same output expression. This is T1 and Q1, and this is T2. So, same thing again. I'm looping this coordinate twice, so it's a 0, this coordinate once, and this coordinate once, so it's a 1. And this x would be a 0 because it's looped twice, and this x would be a 1 because it's looped once. So it's the same expression, KQ2 equals T1 and Q1 exclusive OR T2, and again for the same reasons I've complemented both the outputs so it performs the same function. So KQ2 is T1 and Q1 exclusive OR, not T2. Here we have the countermaps for JQ1 and KQ1. This is T1 straight, T1 there, T1 is a 1 there, and here in KQ1 that's T1 also, so JQ1 equals T1, KQ1 equals T1. So here we have the flip-flop circuit diagram for the Quaternary version. Here we have the JK flip-flops, the Quaternary to binary conversion for the T flip-flop for input T, clock here, which provides these clocks are flip-flops on a negative going edge from a quaternary logic 1 to quaternary logic 0, and that feeds the clock. And this is the logic network that processes the signal. It's an exclusive OR gate, and this is a NAND gate here. This is quaternary to binary conversion, as I explained, and there is a video on it called Quaternary to binary conversion if you want to know more about it. I think that's my 34th video, something like that. Right, so the final thing is the output resistors. 200 ohms resistor there for Q1 and Q2, not Q2, and 390 ohms for Q1 and not Q1. That converts the binary into quaternary. So the output Q is here, and the output Q bar is there. Q bar gives the output 3210 in response to Q being 0, 1, 2, 3 in that order. Right, I have to say all the presentations I've done are on, there's a link in the description for the presentations I've done for all my videos apart from the practical demonstrations, so if you'd like to download it, all you need is Google Drive, and if you've already got a Google account you've automatically got it. So if you want the presentation you can download it, there's a link in the description. Right. Right, this is the Quaternary JK flip-flop. Has the characteristic equation Q plus equals J plus K plus 1 times by Q plus J. This applies to any base. The plus represents a modulo n sum function, and the dot represents the modulo 4 product function, or modulo n product function. So n is 4 in this case, so it's quaternary, but this, like I say, applies to any base, as with the T flip-flop. And Q plus is the value of Q after the flip-flop has been clocked. So I have the quaternary variables here, JK, Q and Q plus, and I've used the same coding for J, K and Q plus as with the T flip-flop. 0, where are we? Yeah, if JK, look at K, 0, 1, 2, 3, 0, 0, 0, 1, 1, 0, 1, 1. So it's the same coding for all the J's, K's, Q's and Q pluses. So again, I'm going to implement it using binary JK flip-flops. So it's the same excitation table as with the T flip-flops. For example, if Q2 is a 0 and Q plus is a 1, and JQ2 is a 1 and an X, and KQ2 is an X. And if Q1 is a 1 and Q plus 1, Q1 plus is a 1, it's JQ1 is an X and KQ1 is a 0. So it's the same coding, and there are no states that you have to take into consideration, because every state is accounted for, every binary logic state is accounted for by a ternary logic state. So unlike the T-flip, the ternary version, it's just a straight conversion. So this is the second half of the truth table. Q equals 2 and 3. J, K and Q as before. Exactly the same coding for J, K, Q2 and Q2 plus and Q1 plus as with the T flip-flop, and the same excited coding of JK for the two binary JK flip-flops. Right. So this is the counter map for JQ2. This output here is not J1, not K1, K2, K1 and Q1. This loop here, these two here, is J1, K, not J1, K2, not K1, Q1. This loop here is J1, not K2, not K1, Q1. And this loop here, these two loops here, J1, K2, K1, Q1. And this loop here of 8 is J2 and not Q1. So I'm going to use some of products to implement the expression to start off with anyway. So this is all of these expressions all together, these min terms, the AND function connects these together and the OR function connects these terms together. So JQ2 equals that, because I've factorised out the Q and then left that there. Now this is the definition of a 3-input exclusive OR gate. So I've substituted J1, K1 and K2 and K1 here with an exclusive OR gate, because that's the substitution, and I've left J2 not Q1 there. So what I'm going to do, because each flip-flop is, each bit is looped once, each one is looped once and not twice, I can change this OR to an exclusive OR gate and use binary Reed-Muller algebra. And I'm using the substitution not Q1 equals Q1 exclusive OR 1 here. So I'm going to expand that out here and then factorise here. So I've taken that Q1 there and used J1, J2, K1, K2 and K1 there as an exclusive 4-input exclusive OR gate, exclusive OR with J2. And then I've complemented each input. So if you complement the exclusive OR gate an even number of times, it performs the same function as when it's uncomplemented. And here I've complemented the output of this exclusive OR twice to give not J2 here. So it just means to say I can use 4 Schmidt triggers instead of 8, because I've made it not K1 or instead of K1, for example. Right. So this is the expression for KQ2 here. Same deal again. This is a 6-variable counter map, and this loop here is not J2, not J1, K1 and Q1. This loop here is J2, J1, K1 not Q1. This loop here is J2, J1, K1 not Q1. This loop here is J2, not J1, not K1, not Q1. And we have a loop of 16, 4 loops of 4 to give K2 and Q1. So these are the terms, the product terms. I'm summing them together in a sum of products expression. All of these terms are odd together. Now I've factorised the not Q1 here to give this, and left the Q2 and K2 and Q1 alone there. Now again, this is the definition of the 3-input exclusive OR gate, so I'll put that there. J1 exclusive OR K2 exclusive OR K1 and not Q1, and then OR K2 and Q1. Now because each variable again is loop 1, each one in the loop is loop once, I can change that OR to an exclusive OR and use binary Reed-Muller algebra. So I've substituted Q1 for not Q1 exclusive OR 1, which is equal to Q1. I've changed that, as I said, to exclusive OR gate. So I've expanded that out times by Q1, K2, exclusive OR K2 there, and I've factorised the Q1 there to give J1, J2, K2 exclusive OR K1 times not Q1 exclusive OR K2. Again, I've complemented each of the inputs 4 times, which is even, so it performs the same function as a non-complemented exclusive OR gate. And again, I've complemented the inputs of this exclusive OR gate twice, once there, and that performs the same function as an uncomplemented exclusive OR gate. So KQ2 equals that. Right. This is the counter map for JQ1, so a hell of a lot simpler. That equals J1, JQ1 equals J1, and the counter map for KQ1, again a lot simpler, equal to K1, so KQ1 equals K1. So this is the circuit diagram for the Quaternary JK flip-flop. Here we have binary to Quaternary to binary conversion here and here. The clocks are flip-flops from the negative transition of a quaternary logic 1 to a quaternary logic 0. This is the exclusive OR gates here, NAND gates here, NAND gates here, and exclusive OR gates here. This is equivalent to a 4-input exclusive OR gate, and these are the expressions. This is output Q1, K1, sorry. So that's a NOT. So I've used an inverter here to convert the not Q1 into not K1 into K1, and that goes to the K1. Yeah, input K1 of the flip-flop here. Same deal with here. That's not J1 there, convert it into J1 there, and this is the expression for J2 here and K2 here. So again, All that's left to do is convert the binary into quaternary. These are 200 ohm resistors, these are 390 ohm resistors, and they convert the binary into quaternary. This is the Q output, this is the not Q output. Again, the not Q output gives the output 3210 in response to a Q being 0, 1, 2, 3 in that order. Right, I think that concludes the video. I'd just like to say I hope you've enjoyed it. Thanks for watching. Bye.